In the last segment, we looked at enthalpy, which is heat of reaction, and entropy, which is a measure of chaos, and see that sometimes it's obvious that reactions do go forward, sometimes it's obvious that they don't go forward, sometimes we're confused. Well, we have to say, well, when is it going to be favorable overall? Well, that's when we calculate Gibbs free energy, which is delta H minus T delta S, and to be favorable, it too has to be negative. So there are a couple of problems here. If a reaction at 350 Kelvin has an enthalpy of 34.5 kilojoules per mole and an entropy of 560 joules per mole degree Kelvin, will it be spontaneous as written? Well, make sure you're understanding about your units. Your entropy is going to be in joules, which tells you qualitatively that it's 3 powers of 10 smaller in unit than enthalpy. Nonetheless, Kelvin will cancel. We've converted this to kilojoules, and we have 34.5 minus 350 times 0.560. And we end up with negative 162 kilojoules per mole. Now that is negative, which would say that delta G is negative and therefore will go forward as written. Well, what gives here? Well, what gives here is that we're at 350 Kelvin. 350 Kelvin is equal to 77 degrees Celsius. That's, give or take, about 180 degrees Fahrenheit. It's like being in a slow oven. So if you think about normal room temperature being about 25 degrees Celsius, this is probably not going to be spontaneous as written unless we heat it up. Okay? All right, let's try the second one. If a reaction has an enthalpy of 4.1 kilojoules per mole and an entropy of 560 joule per mole K, at what temperature will this be spontaneous as written? Well, when delta G is 0, we are at an equilibrium place where it can go either way. So what we want to do is solve for the temperature at which it can go either way and go above that. So again, we're going to convert 560 joules into kilojoules. Okay, and so we're going to end up with 0 equals 4.1. 0 equals 4.1 minus 0.560x. X equals 7.3 Kelvin. Okay, 7.3 Kelvin. Now remember, 0 Kelvin is absolute zero. Okay, the temperature at which molecular motion stops and atoms have no volume. So 7.3 degrees Kelvin is ridiculously cold, like minus 400 and some degrees Fahrenheit. So in order for this to be spontaneous as written, the temperature has to be greater than or equal to 7.3 Kelvin. Okay, so if you think about this at normal room conditions or even in a freezer, that's many, many hundreds of degrees above what's practically 0 Kelvin. So for all intents and purposes, this reaction at room temperature will not be spontaneous as written. Okay? Or will be spontaneous as written because, room temperature is way above that. Okay? This part is much greater than that part. Okay? All right, so page 4, what does this mean? The whole idea is to tell us in delta G equals delta H minus T delta S that usually and typically around room temperature, this is going to drop out. And this is a much bigger driver. So in general, but not always, if delta H is negative, then delta G will be negative. So moving forward, we're going to use enthalpy as a driver of whether reactions will tend to go forward as written. Okay? Now, another concept that we're going to look at is this heat transfer, and we're going to look at this in the lab. But in general, if we're looking for heat that is flowing, it's going to equal m times the change in temperature times specific heat. Now look at the units. Mass is in joule. Temperature is Kelvin or maybe Celsius. Specific heat is generally in joule per gram degree Kelvin. Grams will cancel, Kelvin will cancel, and we have a heat unit. Or we could have mass, degrees Celsius, kilojoule, for example, per gram degrees Celsius. Grams will cancel, Celsius will cancel, and we'll end up with kilojoules. Either way, the Q of the system is the negative of the Q of the surroundings. So if heat is lost by the system, it's a negative here and a positive here. If, on the other hand, if heat is gained by the system, this is a positive and this is a negative. That's the basic premise of heat flow. What's plus to one is a minus to the other. So we'll come back to that when we do our lab with the biodiesel. With that, the next segment will start with reaction rates, equilibrium, and kinetics.